and 1,000,000 times brighter in the infrared wavelength regions. So what this means is that if you were to point your telescope at a distant star, and if you have connected a CCD camera to that telescope, and if you take a picture of that star, even if there is a planet orbiting around it, for every billion photons you get from the star, you'll be getting 1 photon from the extrasolar planet that's orbiting that star. So the brightness contrast is too high. Okay? So the common analogy that people use to describe this is, it's like trying to photograph a firefly that is sitting next to a floodlight. Imagine, consider a 1,000-watt floodlight, like the stadium floodlights that you have. If there is a small firefly that is sitting next to it, you take a photograph of it, okay, the glare of the floodlight will be so high that you will miss the firefly. Okay, so that is the kind of observational challenge that astronomers face when they try to take pictures of extrasolar planets. So all this adds up together. Planets are incredibly small and they are very dim, and these stars and planets are a tremendously large distance from us, which makes direct imaging of extrasolar planets extremely challenging. So whatever I just said is present in this slide. Okay? Planets are much smaller than stars. Far away stars look tiny. Planets orbiting them will appear even smaller. And typically the angular separation between a star and a planet will be less than 1/3600th of a degree, which means these planet and star are going to be very close to each other in the plane of the sky, and stars are usually incredibly bright compared to planets orbiting them. So the planets are easily lost in the brilliant glare of the stars that they orbit. Okay. So all that I summed up is shown in this small animation. Okay, this is an animation. Consider this as a star and this as a planet that's orbiting that star. Okay. Such a system is going to be at light years of distance from us. Just to remind you, light year is a distance that light travels in 1 year. It's traveling at a speed of 300,000 kilometers 1 second. Light takes usually 10 or 100 or 1,000 or tens of thousands of years to reach us from these distant stars. So at those large distances, stars themselves will be point sources and they'll be very bright. So finding planets around them is going to be challenging. So that doesn't mean that it's impossible to find extrasolar planets. Okay. As it turns out, there are some very good indirect ways in which one can infer the presence of planets around other stars. And two of the most successful indirect methods have been radial velocity method and transit method. There are half a dozen techniques, indirect techniques for finding planets around other stars, but among those half a dozen techniques, these two have been the most successful in finding planets, extrasolar planets. Both of them are indirect methods. Okay? And the reason why they are called indirect methods is because using telescopes, we will be observing stars and not planets around them. Based on observing the star and monitoring the behavior of the star, we will make the inference, or we will arrive at the conclusion that there is a planet orbiting that star. So the observation is confined to the star. Okay, we don't see the planet directly, but based on the star's behavior, we infer the presence of a planet around it. So since we do not directly see the exoplanet, this is an indirect method of discovering extrasolar planets. So I'll go through both these techniques. I'll just give you a very superficial, very peripheral overview of what radial velocity method is and what transit method is. During the Q&A, if you have any more questions on this, I'll be happy to answer it. Okay, so first let's take radial velocity method. Before we understand this method, let's refresh the concept of center of mass. I'm sure all of you are very familiar with the concept of center of mass, but just for the sake of revision, let's look at center of mass. So here is a cartoon picture that shows two people sitting on a wooden plank like this. Okay? And if these two people are of equal weight, then the point of balance will be at the center of this seesaw, the center of this wooden plank. Now, if the two people sitting on that wooden plank are of unequal weight, then the point of balance will be closer to the person who is heavier. So this point where the force due to the weight of these people would balance out, that point is what we call as the center of mass of the system. Okay. Now consider a star-planet system like this. The stars are obviously much more massive than a planet. For example, if you take our solar system, the sun is about 1,000 times more massive than Jupiter, okay, one of the most massive planets in the solar system. So since stars are much more massive than planets, the center of mass of a star-planet system will be very close to the star. Okay? Most often, it's going to be almost inside the star. But sometimes, if the planet is really massive, and if it's very close to the star, then the center of mass can be outside of the star. In the case of our solar system, the center of mass between Jupiter and Sun is just outside the Sun. The center of mass between Earth and Sun is inside Sun. Okay? So, depending on the mass contrast between the planet and the star, the center of mass can be sometimes inside the star, sometimes outside. In this particular picture that is shown, the center of mass lies outside the star. And it's usually referred to as the barycenter of the star-planet system. Now, why is this important? The reason why this is important is because we know that the force that keeps a planet in its orbit around a star is the force of gravity. That's what keeps a planet in its orbit around a star. Now, gravity is a mutual force. What that means is the force of gravity that the planet experiences will be the same force that the planet will be exerting on the star. With the result that as the planet goes around the star, the planet will be tugging, pulling the star as the planet orbits around the system. And in reality, what is happening is that the planet is not orbiting the star, but the planet is orbiting the center of mass of the star-planet system. And if the center of mass happens to be lying outside the star, then as the planet orbits the star will also be orbiting around the center of mass. The star won't be stationary, it will be making these small circles with respect to the star-planet center of mass, as shown in this animation. So in other words, the star will be wobbling, okay? It will be oscillating, it will be moving back and forth around the center of mass. It is by observing this wobble motion that astronomers infer the presence of a planet around stars, even if you do not directly see the planet. Now, the way this wobble is measured is, it's measured using telescopes. So what astronomers do is they will be targeting us, they'll be using the telescope to look at a star. And when we look at a star, we won't see it moving back and forth like this. Okay? This is just a computer visualization. The stars are so far away that their small movement with respect to their center of mass will not be seen when we look at it through a telescope. So instead, what astronomers do is they record the spectrum of these stars. And the spectrum will show that the star is not stationary, but it's actually moving. So that's how this wobble motion is measured. It's called the wobble motion, or sometimes it's called the reflex motion, or sometimes very loosely it's referred to as the wobbling. It all refers to this movement of the star around the center of mass, going around in tiny circles. Okay? That's what wobble motion is. Now, let me go a little bit into this spectrum part of this and how the spectra reveals the motion of the star. So just to refresh your memory, I'm sure all of you have done this experiment in school where we split light into different colors using a prism. This is called dispersion of light, and the colored light that you see is the spectrum of this white light. And spectrographs are instruments that are capable of splitting light into different colors like this, light into its component wavelengths. That's what a spectrum is. And so this is what astronomers do with telescopes and spectrographs connected to their telescopes. Using telescopes, they collect light from stars, and that light is fed to a spectrograph. The spectrograph disperses the light and it produces a spectrum of that star. Before I show you the spectrum of stars and how it shows the wobble motion, let me just give you a behind the scenes look at how telescopes look like and how spectrographs look like. This is the Himalayan Chandra telescope. In the previous photograph that I had shown of the night sky, this is the telescope that was there in the foreground. This is a telescope that is owned by India. It's owned and operated by the Indian Institute of Astrophysics in Bangalore. This telescope is situated in Ladakh, which is the northernmost part of India on the Himalayan mountain ranges. And it's on top of a mountain called Mount Saraswati. Okay. If you go inside this dome structure, this is what you would see. So what you're seeing over here is the telescope. As you can see, there's a lot of mechanical structure that goes into the design of a telescope. There's a lot of electronics and instrumentation that goes into the construction of telescopes. So some of you may be studying electronics engineering, instrumentation engineering. Some of you may be studying optical engineering, okay, mechanical engineering, etc. So if you are a specialist in all those areas, your knowledge is of tremendous value for astronomy, because the construction of telescopes, the design of observatories and the building of telescopes, it requires input from engineering significantly. Okay, so this is how the telescope looks like, and the purpose of the telescope is to just collect light. It's a light bucket. It looks at stars, galaxies, and other objects, and it collects light. The light is then sent to either a CCD camera, which takes a picture of the object that the telescope is looking at, or it is sent to a spectrograph, which records the spectrum by splitting the light into different colors. Okay, so I'll show you what an astronomical class spectrograph looks like. Okay, so this is a spectrograph that's called HARPS, High Accuracy Radial Velocity Planet Searcher. It is part of one of the observatories of the European Southern Observatory. You can see a cylindrical structure. All the optical elements that are part of the spectrograph, like the prism and the gratings and various lenses, etc., they are all inside the cylindrical chamber. And once the cylindrical chamber is closed, the pressure inside, the air inside is sucked out, so that you create a near vacuum-like environment inside the cylindrical chamber. That is to minimize turbulence affecting the path of the light beam. And so if you split open this cylinder, you can see what is inside. As I mentioned, there's a lot of optical design that goes into the construction of these spectrographs. And these spectrographs are sometimes connected directly to telescopes. Sometimes they are kept in a separate room. The HARPS spectrograph, which I showed, is kept in a separate room, and the light that is collected by the telescope is brought to the spectrograph with the help of optical fibers. Okay, so there is a lot of engineering that goes behind the scenes of astronomy. So if you are a person with a background in engineering, you can contribute to astronomy instrumentation in very significant ways. Okay, so I just wanted to show you some of these instruments. Anyway, coming back to the radial velocity method. So the way radial velocity method works is, imagine that this is a star, okay, and there's a planet that's orbiting around that star. As I mentioned, radial velocity is an indirect method, which means that we don't see the planet. The observation is confined to the star. So astronomers will be pointing their telescope to stars randomly, and the telescope will collect the light. The light goes to a spectrograph. The spectrograph produces a spectrum, and the spectrum looks like what is shown in the bottom here, this colored band, going from a violet to red. And in addition to these colors, you also see some lines in it. These lines are absorption lines produced by atoms and ions on the surface of the star. So some of these absorption lines could be because of hydrogen atoms present in the surface of the star. Some of these could be due to sodium, magnesium, calcium atoms that are present on the surface of stars. Now, if there is a planet orbiting around the star, then the center of mass of the star-planet system is likely to be outside of the star. And as the planet orbits the star will also be going around in these tiny circles. Now, when we are recording the spectrum, the star is not stationary, it's moving in these tiny circles. So what happens is, sometimes the star will be coming towards us, and sometimes the star will be going away from us. Again, it will be coming towards us and going away from us. Okay? So that will cause these spectral lines to blue shift and red shift. And then again, blue shift and red shift. This is the Doppler effect for light. Okay? If the source that is emitting light is coming towards us, then the light shifts towards higher energies, lower wavelengths, which means it blue shifts. If the source that is emitting light is moving away from us, then the light red shifts, which means it moves towards higher energies, towards the red part. Okay? So this animation shows that. This is just an animation. This is not real data. Okay? This is just a hypothetical star-planet system, and you can see in the bottom that the spectral lines are shifting back and forth. When the star is coming towards us, the lines are getting blue shifted, and when the star is going away from us, the lines are getting red shifted. So by measuring the shifting in the light pattern in the spectrum of stars, astronomers can infer that there is a planet orbiting around it. The bigger the shift in light pattern, the more massive the planet is. The smaller the shift in light pattern, the smaller the extrasolar planet is. And the second thing is, the longer it takes for the light to go through these shifts, one full cycle of blue shift and red shift, the longer it takes for that, the farther away the planet is from the star, and the shorter it takes for the light to shift, the closer the planet is from the star. So by observing the star, okay, by confining the observations to the star, and by seeing this periodic blue shift and red shift, and by doing measurements on that, astronomers can infer what is the mass of the unseen companion and how far away is that unseen companion from that star. This is the essence of radial velocity method. Now, I have to emphasize here that I have only given you a very quick overview of the technique. The actual measurements are far more rigorous. The shift in the star spectrum is very, very delicate effect. It's an extremely delicate effect that astronomers are trying to measure. And this technique, radial velocity method, has been hugely successful in finding planets around other stars. As I mentioned in the beginning of the presentation, the first extrasolar planet around a sun-like star was discovered using this radial velocity method back in the year 1995. The discovery was made by two Swiss astronomers, and they were doing an observational campaign looking at several stars, trying to detect this kind of a wobble motion. And one of the stars that they were looking at is the star called 51 Pegasi, which is a star that is roughly 50 light years away from us. So 50 light years away from us means that light takes 50 years to reach us from that distant star. And so they were collecting light from it, and they were sending it to the spectrograph. And when they analyzed the spectrum, they found out that the spectrum is exhibiting this blue shift, red shift, repeated blue shifts and red shifts, which means that the star is wobbling. It's showing this reflex motion. And that led to the discovery of the first extrasolar planet. So I'll just show you the star's location in the sky. Okay. So this is the great square of Pegasus. If you are interested in night sky observations, you know the great square of Pegasus. So this particular star, 51 Pegasi, is a rather faint star in the direction of the constellation Pegasus. The star is about 50 light years away from us, and in many ways that star is similar to our sun. Okay, the mass and the size and the spectral type and the surface temperature are all very similar to the sun. So this particular star that you see in the center of the animation, that is the star 51 Pegasi. And around 51 Pegasi, they discovered a planet, and that planet is called 51 Pegasi b. Okay. So these are the two Swiss astronomers who made that discovery, Michel Mayor and Didier Queloz, and they were awarded 1/2 of the Nobel Prize in 2019 for the discovery that happened in 1995. So soon after finding this wobble motion for 51 Pegasi in 1995 itself, they wrote a scientific paper where they announced to the world this discovery. So this is a screenshot of that paper, which appeared in the journal Nature back in 1995. The title of the paper says, "A Jupiter mass companion to a solar type star." If you read through it, it says that we are confirming the presence of a Jupiter mass companion to the star 51 Pegasi. The companion lies only 8 million kilometers from the star, which would be well inside the orbit of Mercury in our solar system. So the first discovery was itself a big surprise, because the extrasolar planet that they discovered was completely different from anything that we had known in our own solar system. So here is a planet that's as big as Jupiter, but very close to its star, closer than Mercury is to the sun. Okay, so this immediately threw up a lot of questions, because our idea of how planets form around stars was based on this one example of our own solar system, where all the big gas giant planets are far away from the sun, and the planets which are close to the sun are all rocky terrestrial planets, which are very small. But here in this case, you have a huge planet, probably made of gas, very close to the star. So this led to the idea that this planet probably formed far away from the star, and it has been migrating. The orbit has been slowly decaying, and it has been migrating towards it. So those are some details. Anyway, the first discovery itself threw up a lot of surprises. That's the bottom line of it. Okay, so if this is Sun and that's Mercury, then the star 51 Pegasi has a planet 51 Pegasi b, which is almost touching the surface of the star. So in all likelihood, this planet is not very stable. Okay, its orbit is probably decaying. 100,000 or a few million years from now, the planet may plunge into the star. Okay, the planet probably formed far away from the star, and since then the orbit has been decaying, and we have caught it when it's very close to the star. So now, soon after this 1995 discovery, okay, in the years that followed that, many more extrasolar planets were found using this radial velocity method. And when astronomers looked at the masses of those planets, they found out that almost all the planets that they were finding, they were all big, massive planets like Jupiter, orbiting very close to their stars. Okay. They were not finding Earth mass planets or Venus or Mars-like planets orbiting far away from their stars. And the reason for that is very simple. The reason is because this radial velocity method has an observational bias built into it. Okay. The data that you get from it is skewed, and it is skewed in the following way. Since the detection of extrasolar planet depends on detecting this wobble motion, this back and forth oscillating motion. Okay. If the wobble motion is large, then it's easy to detect it compared to tiny wobble motions. So as shown in this animation, okay, if you have a small planet orbiting around a star, the wobble motion is going to be very, very small, sometimes too small for us to detect. But at the same time, if the planet is really big and if it's close to the star, then the wobble motion of the star is going to be very large, and it will be easy to detect it. So given that the radial velocity method has sensitivity issues, okay, it's much more easier to find massive planets orbiting very close to their stars than terrestrial mass planets orbiting far away from it. So that's the observational bias in the radial velocity method, and that's a limitation of this technique also. It is biased towards finding massive planets orbiting very close to their host stars. So these kind of planets are generally collectively referred to as hot Jupiters. And so if the planet is very close to the star, then the radiation from the star is going to probably make the environment of that planet extremely hostile. and therefore such planets are not likely to be habitable. Okay, such planets are not likely to be places where life as we know it can survive and thrive for millions of years. So just to sum up this radial velocity method, the kind of information that we can gather from this radial velocity technique is, one is we can know what is the mass of the planet, how massive the planet is. We can find out how far away the planet is from the star, and we can find out how long it takes for the planet to go around the star. And lastly, we can also find out whether the planet is orbiting in a circular orbit or whether it's going around in an eccentric orbit. Okay. These are the kinds of information that one can gain from radial velocity method. Now I have to remind you here that this is an indirect method, which means that we have not directly seen the planet. All this information has come about by observing the star. Okay. The second technique that's been extremely successful in finding extrasolar planet is transit method. And in transit method, what happens is, instead of looking at the wobble motion, like in radial velocity, in transit method, astronomers will be monitoring the brightnesses of stars. So let's say that this is a star, and we are monitoring the brightness of the star, okay, how the light that is coming from the star. As we are monitoring its brightness, if a planet happens to pass in front of it, as shown in this animation, then for the duration of this passing by, the duration of this transit, the brightness of the star will dim. So I'll just show it once again. We are measuring the brightness. The brightness is a constant initially, but when the planet moves in front of the star, the brightness dims for the small fraction of time, and then again the brightness picks back to its normal value. So then the next time, if you keep on monitoring the brightness of the star, the next time we will see the brightness dipping is when the planet completes one full orbit around the star and comes back again in front. So repetitive dimming of starlight, repeated dimming of starlight in a very fixed pattern tells us that there is an object that is orbiting around that star that is periodically blocking the starlight. Now again, let me remind you that this is an indirect method. Okay, what you just saw is an animation. It's just a computer visualization of what is happening. In reality, we don't see the planet. Okay. All we are doing is we are monitoring the brightness of the star in it, and the dip in brightness, the periodic dip in brightness, is used to infer the presence of an unseen companion around it. And depending on what is the size of that unseen companion, okay, it's decided whether it's a planet or whether it's some kind of other object. Okay. And so let me go a little bit more deeper into this. So if you have multiple planets going around a star, and if one of them is a small planet and the other one is a really large planet, say one is Earth-like planet and the other is like a Jupiter or a Saturn, then the amount of light that they will block will be different. A small planet will block tiny amount of light. A bigger planet is going to block much larger amount of light. Okay, as shown in this visualization. So the size of the planet plays a role on how much light gets blocked as it transits in front of the star. Now it depends not only on the size of the planet, it also depends on the size of the star. If you have a small star and if you have a planet transiting in front of it, you will get a certain dip in brightness. If the same planet is moving in front of a bigger star, maybe twice the size of this one, so this yellow star is twice the size of this red star, then the amount of brightness dip is going to be smaller. So in other words, the extent to which the brightness of the star dims, that is a ratio that is proportional to the ratio of the size of the planet to the star. The bigger the planet is, more will be the dip. The bigger the star is, less will be the dip. So by measuring the depth of this dimming, astronomers can infer what is the size of the planet relative to the size of the star. Okay, so that's what essentially happens in the transit method. So here is some actual data. Okay, so what is shown here is the brightness of a star along the y-axis and along the vertical axis, and along the x-axis is duration in units of days, and each blue dot here corresponds to the measurement of brightness of a particular star. Okay, so one star, its brightness is continuously monitored, and you see that the brightness is not changing, but suddenly the brightness dips for a small duration of time, and then the brightness comes back up again. Then again it remains constant, then again it dips, comes back again. So how deep this dip is, how much the light from the star dims, that depends on the ratio of size of the planet to the star. So where Rp is the radius of the planet and R star is the radius of the star. So if you can determine the radius of the star, there are some ways for finding the radius of stars, then we can determine the radius of the planet from the depth in the light curve. So even without observing the planet, even without actually seeing the planet, we have already known something about the planet. And generally the duration between two such dips will tell us how long it takes for the planet to go around the star. Okay, now, both these methods, radial velocity method and transit method, both of them are indirect methods where you don't see the extrasolar planet, but there's nothing like actually seeing the planet. What would be really spectacular or what would be really exciting is if we can actually see these extrasolar planets in the images taken by telescopes. And as I mentioned in the beginning of the presentation, there are some difficulties in doing that. But in the last 10 to 15 years, with advancements in optics and design of telescopes, astronomers have been able to take pictures of stars and planets going around them. And so what you're looking at in this slide is a star with 4 planets orbiting around it. So this is real data. In November 2008, a group of astronomers using the famous Keck telescope, which is a telescope located on top of a mountain in Hawaii, and Gemini telescope. Okay, so both these are telescopes which are Gemini telescope is owned and operated by the European Southern Observatory. Keck telescope is owned and operated by the US. So using both these telescopes, this particular star called HR 8799, it's a catalog number for a star. That star was observed, okay, that pictures were taken of that star, and they kept on taking pictures of the star for about 7 years of duration. So it's a long series of observations spanning 7 years, and they used a technique called adaptive optics for it. Adaptive optics is a cutting-edge technique in optics. I'll just quickly explain what adaptive optics means. That is what this AO signifies. So when these telescopes are located on ground, on Earth's surface, the light from these stars, they come through interstellar space, and finally when they enter Earth's atmosphere, the turbulence in the Earth's atmosphere, it distorts the light. It distorts the wavefront of the light, and therefore we don't get a very crisp image of the star. It's like, you know, when you take a dive into a swimming pool, when you're underwater, when you try to look what is outside, you see what is outside, but it will be very blurred out. That's because the water is very turbulent. In the same way, the thick atmosphere, Earth's atmosphere, has all kinds of turbulences in it, which distorts wavefronts of light that are coming to us from distant stars. Adaptive optics, what it does is using control systems. Okay, so this is again coming back to engineering. Okay, those of you are studying electrical or electronics engineering would have studied control systems. So using closed loop control systems, real-time corrections are done to the optics in the telescope to compensate for the wavefront distortions caused by the Earth's atmosphere. So this is very interesting cutting-edge technology, and to a large extent you can compensate for the turbulence of Earth's atmosphere by using adaptive optics. So these Keck and Gemini telescopes are equipped with adaptive optic systems, and this particular image is one of the images that these astronomers took over that 7-year time period. HR 8799 star is what you see in the center. The light from the star has been removed from this. Okay, it's been subtracted out, and if you subtract the light out and if you have a good image like this, then you see these 4 objects marked B, C, D, E. These are 4 planets that are orbiting around the star HR 8799. The star itself is at a distance of 130 light years, 130 light years from us. Now, each of these planets, as it turns out, is bigger than Jupiter, and they are really far away from the star, probably taking several centuries to orbit the star. Okay. If there was a planet that was very close to the star, in this image, it will be very difficult to see it because, as I mentioned in the beginning of the presentation, the light from the star will be so high that the planet will be lost in the glare of the star. Only planets that are far away can be seen through this technique called direct imaging, where we actually see the exoplanet. Now, what I'm going to show you next is, as I mentioned, this HR 8799 was observed for a period of 7 years. So what I'm going to show you next is a animation. This is real data. Okay, this is not computer visualization. This is real data obtained by stitching together all the images that were taken during the 7-year time period. So in the bottom, you see the date, okay, and you will see that the date flips. So this is the HR 8799 star, and these are the 4 planets B, C, D, E. The animation is only 4 seconds long, so just pay close attention. Okay, I'll play it once again. It starts at 2009 and it will end at 2016. So that's 7 years of data all put together to create an animation that's 4 seconds long. And you can see the planets revolving around the star. So this is real data. These are some of the first images of extrasolar planets ever taken. Okay. So each one of them is a planet that's orbiting around that star. I'll show you one more example of direct image, direct photograph of an extrasolar planet. Beta Pictoris is a star, and that star is shown here. The light from the star has been subtracted out. It has been removed. And there is a planet that is seen orbiting that star, and so this is that planet. I'll play the animation. You can see the planet moving with respect to the star. So this is a few years of data. So direct imaging is also now possible. For a small number of cases, astronomers have been able to directly see these extrasolar planets orbiting their stars. But as you can see, it's very difficult. Okay, several years of data is required to create some kind of a visualization like this. Now, the first extrasolar planet around a sun-like star was discovered in 1995. Since 1995, 25 years have gone by, and these 25 years have been a period of great progress in the field of extrasolar planet discovery. In the short span of 25 years, the number of extrasolar planets known to us has swelled in numbers beyond the dozens into the hundreds and now into a couple of thousand. Okay? Today, we know of about 4,200 extrasolar planets orbiting various stars. So prior to 1995, the only planetary system that we knew of was our own solar system. In 25 years, astronomers have discovered more than 4,000 planets orbiting various stars in our own galaxy. So what you are looking at is a histogram map that shows the number of extrasolar planets discovered over the last 25 years. And the colors represent the techniques that are used for finding these extrasolar planets. Red represents radial velocity, green stands for transit method, and the other half a dozen techniques are the other colors. So as you can clearly see, the graph is dominated by red and green. Okay. So that means that 70% of these planetary discoveries have come from transit method. 25% of extrasolar planet detections have come from radial velocity method, and the remaining 5% from all the other techniques, including direct imaging. So in terms of success, radial velocity and transit have been most successful in finding exoplanets. Among that, as you can see from this graph, transit has been really efficient, especially after 2009 or so. Okay? The number of extrasolar planet detections using transit method has really gone up. And the reason why transit has become so efficient in finding extrasolar planets is because of one single mission, which is the Kepler Space Telescope. Kepler Space Telescope was launched in 2009, and it orbited the Earth and the Sun in what is known as the Earth trailing heliocentric orbit. And the mission officially ended in October 2018, so that's roughly 10 years of mission time. And Kepler Space Telescope was a telescope that was built to find exclusively find extrasolar planets using transit method. In this 10-year duration that Kepler mission lasted, Kepler observed about 150,000 stars in a particular direction in our own galaxy. It kept on monitoring the brightnesses of those 150,000 stars and found around 2,600 extrasolar planets. Okay, so we know totally 4,200. Out of that, 2,600 planet discoveries have come from the single Kepler mission. So Kepler was truly a landmark mission. It really changed the field of extrasolar planet studies. Okay, just to give you an idea of how efficient or how impactful Kepler space mission was. Okay, this histogram graph shows the extrasolar planets discovered by Kepler and discovered by ground-based observatories. Okay, so before Kepler, the number of planets that were known with masses and sizes comparable to Jupiter was this blue histogram. Okay, Kepler added a little bit to it, but the area where Kepler really contributed is in the discovery of planets similar to Earth. Prior to Kepler, very few planets of masses and sizes comparable to Earth or slightly bigger than Earth, that's what super Earth means, were known. But Kepler really changed the field by discovering a lot of terrestrial mass, terrestrial size planets orbiting around various stars. And Kepler mission is officially over, but there are many other missions that are planned and some missions which are already up there. TESS is a mission that was launched a year ago. TESS is already there up in the sky above Earth's atmosphere, trying to detect more extrasolar planets using this transit method. And TESS is specifically tuned to detect Earth-like planets orbiting around Sun-like stars. Okay, so there's going to be a lot of discovery that is going to come in the coming years from this TESS mission. And following TESS mission, there are a number of other missions that are lined up for discovering planets around other stars. So let me conclude my presentation. Okay. So this slide, I would like to use it as the final takeaway message of this presentation. Even if you were to forget everything you heard in this presentation, I would like you to remember the following thing. Okay? What research in extrasolar planets of the last 25 years have taught us is that all the stars that we see in the night sky, the innumerable number of stars that we see in the night sky, all of them are likely to have planets orbiting around them. In fact, the statistics suggest that nearly every star in our galaxy is likely to have one or more planets orbiting around it. Okay, it is just a matter of finding them, which, as I mentioned, is not very easy, but not impossible either. Okay, so next time when you look up into the night sky and you see these tiny twinkling stars, imagine within your head that there are planets orbiting around it. Okay, and so what this means is that there are probably more planets in our galaxy than there are stars. Okay? Rough estimates show that there are about 200 billion stars in our galaxy, and it's possible, it's highly likely that each one of those stars have one or more planets orbiting around them. And this is profoundly important because it enhances the odds or chances of finding an Earth-like planet around a distant star that can potentially be a safe haven for life. A planet similar to Earth with liquid water and a dense atmosphere where the phenomenon of life as we know it is a possibility. And what is even more amazing is that the number of stars that astronomers have looked at to find these 4,200 planets is only less than 10% of the stars in the Milky Way galaxy. Okay, so let's say that this is our galaxy, this is the Milky Way galaxy. Okay, we cannot take a picture of the Milky Way galaxy like this because we are inside the Milky Way galaxy. But suppose we could go out of our galaxy and we could take a picture of Milky Way, then it will look like this. Okay, there are 200 billion stars in our galaxy, and our own solar system is not located at the center of our galaxy. We are located about 2/3 the distance from the center, roughly 30,000 light years away from the center. So this red dot represents our solar system's position. All the 4,200 extrasolar planets that have been discovered in the last 25 years have been found by looking at stars within the solar neighborhood. About 10% of the total number of stars in the Milky Way. So even our own galaxy, we have not surveyed completely. Okay, so this is really interesting because, as I mentioned, it feeds into this question of finding an Earth-like planet in our own galaxy, orbiting a sun-like star, which is potentially a place for finding a life, okay, where life can arise. So I finally want to end this presentation with a very famous quote from the science fiction writer Arthur C. Clarke. Okay, so all of us are interested in this bigger question of whether we are alone in this universe. Is there a possibility of life elsewhere in this universe? As of now, there is no conclusive evidence for the presence of life outside of Earth. Okay. Within our own solar system, space scientists have looked at Mars. They have looked at some of the moons of Jupiter, Saturn, etc. to see whether they can identify microbial life. The search within our solar system itself has not been done very thoroughly, but so far there has not been any conclusive evidence for the presence of life in any of the other planets within the solar system. In the case of extrasolar planetary systems, we are just at the doorstep of this discovery. Okay, we are at a place where we are just beginning to detect these extrasolar planets, and we are far from answering the question whether any of these planets could be supporting life. Okay, so that is probably the next step, and there are some observational ways in which that can be tried and tested, okay, which I have not covered in it. But anyway, I think as of now there are two possibilities. Okay, either we are alone in this vast universe, or there's a possibility that we are not alone, and both are equally exciting. So I will conclude my presentation with this, and if you have any questions, you can ask. Over to...
Thank you.
Yeah.
Thank you, sir. Sir, we have received some questions in the chat box, but before that, anyone wants to directly ask the question? Okay, then we move on to the chats. Okay, Abarna KP has asked 3 questions. So, Abarna KP, can you please unmute your mic and ask the question?
Hello, sir.
Yeah, yes, Abarna.
Sir, I have a number of questions.
Yeah.
The first question is, sir, can we find the number of planets around a star using the radial velocity method? Because radial velocity method gives the mass idea of the star, but a planet. But can you find the number of planets around a star?
Yes. So that's an interesting question. Something which I did not cover in the presentation. Okay. So multi-planetary systems can also be discovered using radial velocity method. So what happens is, I did not go into the nuts and bolts of it. Okay, so what happens is that when astronomers record the spectrum, they see the spectrum shifting towards blue and red, and this extent of shift will have different periodicity corresponding to different planets. Okay, so just to give you an example, if you take our own solar system, there is Sun and there is Earth and there are other planets, but for the sake of simplicity, let's just take Sun, Earth and Jupiter. Okay. So the Sun, there is Earth and there is Jupiter. Jupiter takes about 11 Earth years to go once around the Sun. Earth takes 1 year to go once around the Sun. So if you are an alien astronomer sitting in some distant star, okay, in a planet that's orbiting a distant star, and if you were to use radial velocity to look at our own solar system, then you will find that the spectral lines, the spectrum is shifting with a periodicity of 11 years. Within that 11 years, you will see a superposition of a shift corresponding to 1 year. And the 11-year shift will have a certain amplitude, and the 1-year shift will have a certain other amplitude. So it's like a superposition of harmonics that you see in the data. And once that radial velocity data is obtained, astronomers try to fit Keplerian models to the radial velocity data, and they will look for harmonics within the data to see whether the wobble motion is due to one planet or whether it is due to multiple planets. So this is a 1 minute answer to your question. So just to sum it up, what it means is that it's not just the mass of the planet that can be detected, but also the number of planets that can present can also be found. But again, it depends on the sensitivity of observations. For example, an Earth-like planet orbiting around a Sun-like star would produce a wobble motion that is of the order of centimeters per second. The velocity of the star will be changing by about centimeters per second. Whereas a Jupiter mass planet would cause a wobble motion that is several tens of meters per second. So from an observational point of view, it is easy to measure meter per second and centimeter per second. So if your observation is not really good, then you will miss out on most of the planets in the planetary system, and you will end up only finding the massive ones. So that's where radial velocity is skewed or biased towards finding big planets. But to finally answer your question, it is possible to find multiple planets.
Okay, sir. Thank you so much. Sir, my next question is, sir, you talked about transit method. Can we find the atmospheric composition of the extrasolar planets by taking the spectrum of the transit method?
Yeah. So So have you read about this somewhere else?
Yeah, I've read it, but I'm not really clear about it. I've read it somewhere.
Yeah. So this is the frontier field in extrasolar planet studies. Okay. So in transit method, now it's not just possible to find the size of the planet, but also one can also see whether the planet is supporting an atmosphere. Now, this is not possible for every transit detection. Some cases it is possible, and the reason why the detection of atmosphere is so important is because if you look at our own solar system, Mars, Venus and Earth, they are all similar in their masses and sizes. Okay, Mars is a little bit smaller, but if you ignore it, they are all comparable in sizes and masses. But if you look at Venus, Venus's atmosphere is dominated by CO2 and sulfuric acid, H2SO4. Mars's atmosphere is also dominated by CO2, whereas only on Earth, oxygen is present in such high abundance. Okay, oxygen is 20% of Earth's atmosphere, which is 1 part in 1/5. Okay, so that is 1/5, that is 20%. And the reason why there is so much of oxygen in Earth's atmosphere, molecular oxygen in Earth's atmosphere, is because Earth has a biomass. There is life present on Earth. In fact, the oxygen abundance in Earth's atmosphere increased after photosynthetic algae, okay, small microbial life forms that produce their energy through photosynthesis after they formed on Earth, roughly 3 billion years ago. So in the very distant past, okay, Earth's atmosphere was very similar to that of Venus and Mars, predominantly made of CO2, etc. But once life appeared, slowly the abundance of oxygen started increasing. So the presence of oxygen, water vapor, ozone, etc., these are indicators that the planet may be having a biomass, a biosphere, where life is present. So detecting molecules in the atmospheres of these extrasolar planets is something that astronomers are trying, and it has been, they have succeeded in a few limited number of cases. So what happens is, the technique is as follows. As the planet moves in front of the star, the planet is blocking a little bit of light. But some of the light passes through the atmosphere of the planet. Okay? So if you take spectrum of the star, when the planet is transiting, then in that spectrum of the star, we will see absorption produced by chemical elements, molecules present in the atmosphere of the planet. Once the planet moves out of the way, the absorption due to those chemical elements will vanish from the spectrum. Again, when the planet is transiting, if you record the spectrum of the star, you will once again see those absorption lines. So this shows that these absorption lines does not belong to the star, but they belong to the atmosphere of the planet. Okay, the gaseous tenuous atmosphere of the planet. So using this, astronomers are trying to see whether they can detect water vapor, oxygen, etc. from these exoplanet atmospheres. These kind of molecules which are indicative of life, they are called biomarkers. Okay. So this is an up and coming field in astrophysics. In the next 10 years or so, we are likely to see a lot of interesting developments happening in this. It's a good question, Aparna.
Thank you, sir. Sir, just one more question. Sir, what are the chances of finding planets around binary stars?
Okay, so it's a bit tricky because the binary stars are two stars. Sometimes you have triplet star systems where you have three stars going around the common center of mass. So the stars themselves are wobbling because of mutual gravitational force between the stars. On top of that, if you have a wobble motion produced by a planet, it's usually very difficult to see, but it has been seen. For example, the star system that is closest to us, closest to the sun, is Alpha Centauri, Proxima Centauri, which is a triplet star system, which is about 4 light years away. And using radial velocity method, astronomers have found extrasolar planets around them. So that means that planets, it looks like planets can indeed form around multiple star systems. It will be a very bizarre scenario because, if you are living on one of those planets, you will see multiple suns. Okay, so there will be a sunset and immediately there will be a sunrise, and then one more sun will come up in the sky. So we can only speculate on how conditions would be on those planets. But from an observational point of view, yes, astronomers have found extrasolar planets around binary stars. Okay, the closest example is Alpha Centauri, Proxima Centauri system around which planets have been found.
Thank you, sir. Thank you so much.
Yeah.
Okay. Now, Archana Lakshmi has asked, are exoplanets habitable ones? I think Sahar has covered that.
Yeah, so I'll just quickly mention many of the planets that Kepler mission has discovered. Many of those planets lie in the habitable zone of the star. Okay, so there is an interesting concept called habitable zone. Habitable zone is the distance from a star where water can exist in liquid form. So the definition is based on the premise that water is an essential ingredient, or water is a prerequisite for life as we know it. Okay, on Earth, at least, life depends heavily on water. The first forms of life formed not on land but on water. So if you consider that water is a prerequisite for carbon-based life, then finding water is very important, and therefore astronomers have come up with this small calculation where we can calculate at what distance from a star would the temperatures be conducive, would the temperatures be favorable for water to exist in liquid form, which means where the temperature will be between 0 degrees centigrade and 100 degrees centigrade. Lower than 0 would mean that water will be in solid form as ice, and greater than 100 degrees centigrade would mean water will be in the vapor form as water vapor. So there is a sweet spot, okay, a sweet spot from which a distance from a star where water can exist in liquid form. This is called habitable zone. And for all the extrasolar planets that have been discovered, astronomers have also calculated whether they lie within the habitable zone or not. And there are a lot of planets which lie within the habitable zone. Okay, so it's very interesting, but the presence of water does not just depend on how far away a planet is from the star. It depends on whether the planet has an atmosphere or not. Okay, for example, Jupiter has a moon called Europa, and Europa, this moon of Jupiter, is entirely made of water ice. And we know that on Earth, whenever you have water ice, there is liquid water underneath it. So there is probably liquid water in Europa, which is a satellite of Jupiter, even though the satellite is very far away from Sun. So distance from the star is not the only criteria, but it's one of the criteria. And using that, this question of habitability has been looked at. Next question.
Okay, sir. Next question, Kashmira has asked that does Sun have an orbit like 51 Pegasi?
So I think, Kashmira, what you mean is that does the Sun wobble like, does it exhibit a wobble motion, this oscillation motion like 51 Pegasi? So it does not, because 51 Pegasi has a huge planet of the size of Jupiter sitting very close to that star, 51 Pegasi. In the case of our solar system, all the big planets are much further out, which means that the center of mass is very close to the sun. So it's not going to exhibit such a wobble motion. In fact, if you are an alien astronomer and if you use the radial velocity method with the kind of sensitivity that we have right now, if you were to look at our own solar system from a large distance, we are not likely to find any planets around the sun. Okay? Because the wobble motion produced by all those planets are very, very small. We may detect Jupiter and Saturn and Neptune, but it will be very hard using current techniques to find Earth or Venus or Mars or Mercury around the sun if you were to look at our solar system from a distance. So 51 Pegasi's wobble motion is not like the sun's wobble motion.
Okay. Rakesh has some doubt in the presentation. So can you please unmute and ask?
Hello, sir. I am Rakesh. Sir, in
Yes,
one
Rakesh.
of the slides that you have shown in that beta Pector sp system, the planet seems like moving towards the host star. So I was wondering why it is moving like that.
Yeah, so that is just a projection effect. Okay, we are looking at a 3D thing in 2D. So for example, if this is the star,
Okay.
and if the planet is going around like this, okay, planet is going around like this, then as the planet goes behind the star, from your point of view, you will see that the planet is coming towards the star. But actually the planet is orbiting around the star like this.
Oh, okay. So
So
when
it is 3D, but we are seeing it in projection in 2D.
okay, got it, sir. Thank you.
Yeah.
Vishnu Mohan has asked some couple of questions. So please unmute and ask.
Hello.
Yeah, Vishnu, yes.
Thank you, sir. Thank you for your presentation. I have some questions. Can I ask?
Yeah, sure. Go ahead.
Yes, first question is actually how the internal structure of a star is analyzed actually, other than the surface composition. How we are getting an idea about the internal structure of a star.
Yeah, so it's not very easy to analyze the internal structure of a star. Okay, so usually this comes from oscillations that happen within the star. So there are disturbances that propagate through the interior of a star. These disturbances are like sound waves that propagate through a medium, and that they cause oscillations on the surface of the star. So these oscillations are monitored, and from there are radial oscillations, there are transverse oscillations, etc. And it's like seismology. So for example, how is the internal structure of Earth known? Okay, seismology, that is tracking the small vibrations that happen on the surface of the Earth, small tremors that happen on the surface of the Earth, is one way to understand the internal composition of the Earth. In the same way, there is a branch of astronomy called helioseismology, which looks at these kind of perturbations that happen on the surfaces of stars, particularly the sun. Okay, we can do this very well for the sun because the sun is a huge object. By looking at small perturbations that are coming on the surface of the sun, one can understand what is likely to be the internal composition of the sun. And it is consistent with being plasma, highly ionized matter. And in the inner core of stars, nuclear fusion reaction is happening. And the way we know that there is nuclear fusion happening in the inner core of stars is, including the sun, is that using atomic physics, using nuclear physics, astronomers have written down the kind of possible nuclear reactions that can happen in the core of stars. Okay, they have written down a large number of reactions that are possible. And some of these reactions come up with certain byproducts like neutrinos. So when hydrogen nuclei, when protons fuse together, one of the particles that is produced is a neutrino. And it's a particular flavor of neutrino. And when we observe stars like the sun, we see neutrinos coming from the sun. And these neutrinos are the only place where these neutrinos are likely to be produced is a place where nuclear fusion is happening, and therefore we know that there is nuclear fusion happening in the interior of the sun. So helioseismology plus nuclear physics, etc., is what is used to understand or make an educated guess on what happens in the interior of stars.
Thank you, sir. Thank you. I will quickly jump on to the next one.
The answer. Yeah.
Sir, can I ask the next question, please?
Yeah, but before that, you ask the crow to leave. The crow is making a lot of noise.
Oh, sorry. Yeah.
Is it your pet crow?
No. I was sitting outside actually. Okay.
Go
So
ahead.
can you hear me, sir?
Yeah, I can.
Yes. My next question is actually how were the first stars in the universe formed? And when there was only hydrogen and helium around, and what caused the disturbance for matter to accumulate? Then, as there was no supernova around then at that time, right? So to initiate a disturbance for matter to clump together, what was the initial means at the time of the universe formation? There was no other stars, no. So there was only hydrogen and helium. So how were the first stars formed, and what caused the disturbance for the matter to accumulate? And in recently I read that actually stars were formed when any disturbance happened in the molecular clouds and all. So at that time, how was the first stars formed?
Okay, so this is a semester-long course in itself, the formation of first stars. Okay, I don't know whether I'll be able to give a coherent answer in 1 or 2 minutes, but I will make an attempt. Okay, formation of first stars is an ongoing field of research in astrophysics. Not all details have been worked out, but you are right. Okay, in the Milky Way galaxy, there is star formation happening. And those kind of star formations happen when there is some disturbance or when there is some perturbation that causes huge portions of huge gas clouds to fragment and collapse. Now, in the early universe, these kind of perturbations are likely to have been provided by something called acoustic waves, which were present in the initial primordial soup, which constituted fundamental particles and photons. So these acoustic waves are, once again, as I mentioned in the case of interiors of stars, these are disturbances that are produced by something called quantum fluctuations in the early universe. So quantum fluctuations you can think of as disturbance of perturbations in space-time, and these perturbations in space-time caused ripples in space-time, which resulted in certain parts of the universe getting compressed and certain other parts getting decompressed or rarefied. And so the compressed regions constituted the regions where structure formation happened. Galaxies, stars, star clusters, etc. formed. So this is the short answer to your question. So as you rightly said, there were no supernovae when the first stars formed. So the trigger for the formation of the first star came from the primordial universe itself. Okay, so that's the short answer, but it requires much more elaborate discussion to give you a full answer for this.
Yes, sir. I will refer to quantum fluctuations. Sir. Thank you, sir.
Yeah.
And I will quickly jump to the next question. And what is the maximum number of stars in a star pair that we have discovered?
In a star pair?
Maximum number of stars that can be together in a star pair.
Okay, I don't know the number, but I think it is 3. I don't know whether there are 4. See, there are some objects called star clusters, which are gravitationally bound systems of stars. Our sun doesn't live in any star cluster. Sun is an isolated field star, but there are groupings of stars which are bound by mutual gravitational force. These are called star clusters. And some of the densest star clusters have up to 1 million stars in them. So if you want, you can refer to it as a bundle of stars with millions of stars together. And there are many such star clusters in our own galaxy. So that could be one number. But if you're talking about double, triple star systems, then I think maximum is 3 that I'm aware of. Okay, I'm not entirely sure. Outside of star clusters, the number of stars that are gravitationally bound are usually 2 or 3.
Yes, sir. And next question, sir. whether all the planets around the mother star have the same direction of revolution. Any exceptions?
So most likely, the direction of revolution is going to be the same. That is due to the conservation of angular momentum.
Yes.
Okay, so to conserve angular momentum, it requires that all the planets form in a disk around the star. So you don't have planets with orbital planes with random orientations. All the orbital planes are more or less in the same plane. And all of the planets will also be orbiting in the same direction. That is because the ingredients from these planets, ingredients that went into the formation of planets, they were all orbiting around the star in the same direction to conserve angular momentum of the collapsing cloud from which it formed. So it's highly unlikely that you will find a planet that is orbiting in the opposite direction of the other planets.
Any exceptions? Have you ever found any star, any planet like that?
No. So I don't see these extrasolar planet detections are just coming out, and I don't think people have looked at multiplanetary systems trying to see whether they are going one way or the other. Because the direction of motion, I don't know whether we can detect it from the radial velocity data.
Yes. And next question is, whether the presence of liquid water is the only feature that we are looking out for exoplanetary life. Are we skipping the chance that the alien biology could be entirely different than water-based?
Yeah, so that's a good question. See, this is really a very simplistic search for life, and we can only look for something that we know. And the only example that we have of life is life on Earth, okay, carbon-based life that depends on liquid water. In fact, we don't even have a comprehensive definition of what life is. If you ask, if you search, you will not be able to come up with a good comprehensive definition of what life is. Okay, so every definition that you come up with is likely to have exceptions within Earth itself that violate that definition, which are still life. Okay, so given that our own incomplete understanding of life here on Earth, okay, it will be too far-fetched to think about other kinds of life. So right now, the search for habitable environments depends only on the kind of life that we are familiar with here on Earth. But in addition to this, okay, since you asked that question, in addition to water-based life, carbon-based life, etc., there is another kind of approach that astronomers have been pursuing for the last 50 years or so, which is called the SETI program. I don't know whether you have heard of it. Have you heard of this, Vishnu?
Yes, I have heard. Search for extraterrestrial intelligence. Something like
correct. So, search for extraterrestrial intelligence is a really far-fetched observational campaign to detect messages beamed towards us by intelligent civilizations elsewhere in the universe. So there we don't make any assumption on what kind of life it is. We don't make an assumption on whether it is carbon-based or whether it is water-based, etc. The only assumption that is made is that it's intelligent enough to be broadcasting itself into outer space. Okay, so but not many astronomers are involved in that program because, as you can rightly guess, it is a program for which you can never define when it's going to end. Okay, so you have to keep on looking for it. Therefore, it is not in the mainstream of research in astrophysics, but there are a handful of people who are doing it. So these are the things which I know of where the possibility of life has been looked at.
Yes, sir. Just two more questions, sir. I will be very quick. And why we find gas giants in the outer orbits and small terrestrial planets in the inner orbits?
Okay, so that's a good question. Okay, now I can split it into two. One is why are terrestrial planets small and gas giants big? And the other question is why are gas giants far away from the star and why are terrestrial planets close to the star? Okay, so the first question I will answer: why are terrestrial planets like the Earth always small in size compared to gas giants like Jupiter? So these terrestrial planets like Mercury, Venus, Earth, and Mars, they are made up of heavier elements: okay? Aluminum, silicon, magnesium, iron, etc. And the gas cloud from which the sun formed and the planets formed around the sun, that gas cloud was predominantly made of hydrogen and helium. It had only trace amounts of heavier elements like aluminum, silicon, magnesium, sodium, potassium, etc. So the inventory of heavier elements was very less in the gas cloud from which the sun and the planets of the solar system formed. So if you have only small amounts of heavier elements, then the planets that form out of the heavier elements has to be small. You don't have an unlimited supply of iron and silicon and magnesium. Okay, vast majority of the composition of this cloud is hydrogen and helium. That's why gaseous planets are bigger and terrestrial planets are smaller. The other question is, why are the gas giants far away from the star and why are the terrestrial rocky planets close to it? The reason is, if you are close to a star, then the amount of radiation, the heat and light that you are going to get from that star is going to be high. If you are far away from the star, the amount of heat and light that you're going to get will be smaller. Now, for planets to form, these molecules have to condense to their solid forms. Now, gases, they are volatile by their very nature, which means that if the temperature is even a little bit higher, this hydrogen and H2O and all these things are going to exist as water vapor. They can condense into solid form only far away from a star, whereas non-volatile elements like iron, magnesium, silicon, sulfur, potassium, calcium, etc., they have high melting points, which means that even at regions close to a star, they can exist in solid form. Okay, so that's why terrestrial planets can form closer to the star. Terrestrial planets can also form far away from the star, but gas giants, okay, because of the radiation pressure from the star, all the gases are pushed to the outskirts of the planetary system, and in the outskirts, these gases and ices, they can condense to form solids. Okay, they can group themselves together under self-gravity to form spheres, and that's why gas giants are formed in the outskirts. So this is the answer to your question.
Yes, sir. Just from your answer, I just got one more doubt, sir. What about hot Jupiters? Hot Jupiters mean that they are hot, right? So why the volatile gas is not evaporating away?
Yeah, so I showed you the screenshot of the paper that Mayer and Kulos published, and the abstract, the last line says that the only way that this 51 Pegasi b, this hot Jupiter, can be present so close to the star is if the planet is migrating. So there is a new idea that has come up in exoplanet studies because of research in exoplanet studies, which is planetary migration. And what it means is that when a planet forms around a star, the planet may not form in a dynamically stable orbit around the star. Okay, so the planetary orbit may not be dynamically stable, and which means that the planet will slowly, the orbit will slowly decay over long time periods, and the planetary orbit, the planet will move closer and closer to the star as the orbit decays. And finally, you know, when the hot Jupiters that we are detecting, these are all planets that have come very close to their star, and far into the future, they may actually plunge into the star. They may go and hit the star. So the hot Jupiters, they did not form very close to the star. They formed farther away, but they were not in dynamically stable orbits, and therefore, because of orbital decay, they are moving closer and closer to the host star. That's the idea.
So
otherwise, there is no way. Otherwise, there's no way a gas giant planet can form so close to a star. There is no way that, because people are studying planet formation using computer simulations. Okay, there are large-scale computer simulations where people look at how planets form around stars, and all those simulations show that gas giants can only form far away from a star where conditions are favorable.
Yes, sir. So that hot Jupiter was once a cold Jupiter, and as its orbit got degraded, it became a hot Jupiter, right, sir?
Correct. So in our own solar system, it's likely that our solar system had many more planets than what we see today. Not all of them were in dynamically stable orbit. Some of them were in unstable orbit, and it's likely that they would have plunged into the sun in the past history of our solar system. What we are seeing now is a cleaned up solar system where all the objects are more or less in stable orbits. Even now, there are some comets which are in dynamically unstable orbit. So every now and then, every few months or few years, we can see comets going and plunging into the sun. That is because they are in dynamically unstable orbits.
Yes, sir. Thank you, sir. And my last question here it is, sir. And
Yeah.
is there a course called astrobiology, and what does it deals about?
So the discovery of extrasolar planets has kindled a lot of interest in this question of whether it is possible to find the presence of life outside of Earth. And from that, this interdisciplinary field of astrobiology has come about. Okay, astrobiology is a happy marriage between astronomy, biology, atmospheric science, planetary geosciences, and geology. So to address this question of whether there could be life elsewhere in the universe, astronomers can only tell you whether there are planets present around other stars, and they can also tell you how big those planets are, how massive they are, how far away they are. Within our solar system also, astronomers can only tell us what the planets in our solar system are. You need a geologist to be able to tell whether the surface conditions on a planet are favorable for life. You need an atmospheric scientist to tell whether what role does an atmosphere play in the evolution of a planet in the presence of life in it. So atmospheric scientists are also contributing. And finally, since the object that we are looking for is the phenomenon that we are looking for is life, you need a biologist to tell what constitutes life, what are the environments in which life is likely to thrive, what are the environments in which life is likely to evolve, and in what conditions are favorable for life. So there are scientists working in all these disciplines, scientists who are experts in all these disciplines coming together into this field called astrobiology. And it's a mainstream research area right now. Okay, there are astrobiology research institutes abroad. And if you look at the kind of people who are working in these institutes, you will find biologists, astronomers, geologists, planetary scientists all working together to address this common question.
Yes, sir. Yes, sir. And is there any institute in India that deals with astrobiology, sir?
Currently, there are no institutes which offers a program in astrobiology. Some of the institutes are offering courses in astrobiology, where, for example, IIST offers an institute elective on astrobiology, which is taught by 5 faculty members. There is an astronomer who teaches extrasolar planets. There is a chemistry person who teaches astrochemistry and biochemistry, which talks about the prevalence of organic molecules in the universe. Then there is a geologist who talks about comparative planetary sciences. Okay, then there is another chemistry person who talks about life in space. In that module, the kind of experiments that happen in International Space Station, okay, to grow plants, look at the growth of bone cells, they look at the growth of cell multiplication, etc., in neutral buoyancy conditions, which means in space, those kind of things are done. So these kind of courses are taught in some select institutes in India, but there is no astrobiology research program as such.
Yes, sir. Yes. Thank you so much, sir. Thank you so much for your elaborate explanation, and that too in a simple manner, sir. Thank you so much, sir.
Yeah, good questions. Thanks.
Thank you, sir.
Okay. So Amaldev has asked one question. Can you please unmute and ask?
Okay, sir. Hi. Okay.
Yeah, hi.
Okay. How does the orbital plane of the exoplanet system affect these methods you mentioned?
Yeah, so that's a very good question, Amaldev. So, see, I don't know whether you can see this. I'm trying to show it on my webcam. So, if you have a star like this, and if let's say that you are the observer, if you have a planet going around the star like that, then the wobble motion will be towards you and away from you, towards you and away from you for the star. Okay, which means if you are recording the spectrum, then you will see blue shift and red shift. But if the planet is going around like this, around the star, then the wobble motion will be perpendicular to your line of sight. So this kind of a wobble motion, you will never have a scenario where the star is coming towards you or going away from you, but instead the star's orbit will be orthogonal or perpendicular to your line of sight. So which means even though the star is wobbling, the velocity vector is not pointing in our direction. So such kind of planetary systems will escape our detection. We will not be able to detect them through radial velocity method. If the planet is going around like this, we will not be able to see it using transit method also, because for transit to happen, the planet should move in front of the star. So if you have an orbital plane that is in the plane of the sky, then those planetary systems we cannot detect. So that is another observational bias. Both radial velocity method and transit method are biased towards finding planets that are perpendicular to the plane of the sky. So planetary systems where the orbital plane is along our line of sight.
Okay, so one more question. How do you simulate all these planetary situations? Like, what software do you use?
Okay, so most of these things you can write your own. The visualizations that I showed in the presentation, they were all taken from internet. Okay, so there's plenty of material available on internet where you can see these visualizations. But in the research side, when people want to simulate star planet systems, it is you can do it very easily. All that you need is you need to define the mass of the star, the mass of the planet, and the orbital separation between them. After that point, it is just basic laws of gravity. The planet, the only force that is acting between the star and the planet is the force of gravity. So once you know what that force is, you can always calculate what is the velocity of the planet around the star. How long does it take? Kepler's third law will tell you how long does it take for the planet to go around the star. So it's basic orbital mechanics. It's very easy to simulate these things.
Okay, sir. Thank you.
Yeah.
Okay, now Joe Augustine has asked 2 questions, so you may please unmute and ask directly. Joe Augustine.
Joe Augustine, I think.
What's up?
Joe Augustine, right?
Yeah, sorry, Joe Augustine. Sorry.
Joe Augustine, are you there?
I think he left.
So Joe Augustine has a question. How can we be sure that the wobbling motion of a star is due to a planet and not due to another star? Okay, so that's very simple. Okay, so the wobble motion, from the wobble motion, we can infer the mass of the unseen companion. If the mass of the unseen companion comes out to be 1 solar mass, or 1.5 solar mass, or 2 solar mass, or 3 solar mass, which means 3 times the mass of the sun, or 1.5 times the mass of the sun, or equal to the mass of the sun, then it is likely to be another star. If it is 2 or 3 times the mass of the sun, then it could be a black hole. Okay, just because we don't see something doesn't mean that it has to be a planet. You can also have a black hole going around a star. So the mass is what helps astronomers to discriminate between a planet and a star. If the mass of the companion from the wobble motion of the star, if the mass of the companion comes out to be the mass of Jupiter, or less than the mass of Jupiter, or 10 times the mass of Earth, then it cannot be a star, because you cannot have a star with such a low mass. It has to be a planet. So the value that we estimate for the mass helps to discriminate between a planetary companion and a stellar companion. Maybe
Okay,
one last question.
Yes, we have the final question from Vishnu Murthy. You can unmute and ask.
Good afternoon, sir.
Good afternoon. Yes, Vishnu.
Yeah, I was just wondering how the sizes of the stars are measured. Not the mass, but the sizes.
Okay, so as it turns out, the mass, the size, the surface temperature, and the luminosity of a star, these are all related to each other. Okay, stars of a certain luminosity and mass will have a certain size. So if you can find out how luminous a star is and how massive it is, then we can infer its size, because all these parameters are mutually linked. A massive star will have a high surface temperature and is likely to be bigger and will be very luminous. A low mass star will be small in size, will have surface temperature that's very low, and will be dim in brightness, which means less luminous. So these parameters are interlinked, and that is because stars are the the stars, they behave like black bodies. Okay, and in black body, the mass and size and surface temperature and luminosity, these are all interconnected. There are some physical laws that govern it. So by measuring the brightness of a star, calculating its luminosity, its intrinsic brightness, and by measuring its surface temperature, one can infer its size. That's how the sizes of stars are determined.
All right, thank you.
Thank you. That's all, I guess, right?
Yes.
Yes.
So I think that is the end of the questions. So let's conclude the session. Over to you, Adrika.
Thank you. Thank you, Aslam, for moderating the questions. Sir, even though this was a very vast topic, you concluded it into, you put this all information into a pack of 1.5 hours, even answering all the queries very patiently. Thank you, sir, for doing this for us. We are very happy for starting NOVA as a Space Week celebration with such an eminent personality. Even though we went through complex science and discovery procedures, the main element I found inspiring was that very basic concepts in science we left in school time is being used for such vast discoveries. It was indeed very much inspiring for us. Thank you, sir. Thank you so much for the session.
Yeah. Thanks, Adrika. It was my pleasure. And thanks to NOVA. Wish you all the best in your future sessions also. Okay. And I don't know, some people have logged out, but for those who stayed back, I have a bonus 2 or 3 slides. Okay. So just give me 2 minutes for that.
Definitely.
Since we were talking about planets, okay, I just want to leave you with a couple of images. Since most of you are astronomy enthusiasts, I'm sure you may have seen it. I'll just share these 1 or 2 slides. I think it's worth. So am I presenting even now? I think so.
Yes, sir.
Yeah, I'll just present it. Yeah, just hold on. So since we are talking about extrasolar planets, finding planets around other stars, just to give you an idea of how vast a universe we are living in and how tiny our own position is in it. Is my slide visible?
Yes, sir. Yes, sir.
It's visible. So this is a picture of the Earth taken by one of the Apollo astronauts. So from the distance of Moon, Earth looks like a blue marble. Okay, and which tells us that water is an abundant molecule in Earth's atmosphere. There is no other planet that looks this blue in color. But if you travel further away, okay, the Earth looks even tinier. I'm sure most of you have seen this picture. Okay, this is a picture of the Earth taken by the Cassini spacecraft. Cassini was a probe that was sent to study Saturn and the satellites, the moons of Saturn. So this black patch over here is Saturn, and the light from Saturn is blocked out. Otherwise, it will be too bright to see whatever is in that image. These are the rings of Saturn, and down below, this bright pixel over here is Earth as seen from the distance of Saturn. Okay, but this is not the farthest picture that we have taken of Earth. Does anyone know the farthest picture of Earth taken? Which spacecraft has taken it?
Pale blue dot.
Yeah, exactly. So as I said, most of you already know it. So this may be redundant information, but still. Okay, so Voyager is the spacecraft that has taken the farthest picture of the Earth and also other planets of the solar system. As you know, Voyager, there were 2 missions. It was a twin flyby mission to study the outer planets of the solar system, launched in 1977. And about 30 years ago, okay, when Voyager was in the far outskirts of the solar system beyond the orbit of Pluto, the spacecraft was asked to turn back and take a snapshot picture of the Earth, which has become very famous. Okay, so this is that picture, as somebody just said, pale blue dot. Okay, so what you're seeing in this is the black emptiness of outer space, and this red band is scattered light in the camera optics of Voyager. So this is an artifact. Okay, this is an artifact due to the optics of the camera itself. But in the center of it, you can see a bright pixel. So that is Earth as seen from beyond the orbit of Pluto. Okay, this image was taken on February 14th, Valentine's Day, roughly 30 years ago. So this February 14th, 2020 was the 30th anniversary of pale blue dot. Okay, and so this is like a global selfie. Okay, this is a selfie that includes all of us. Okay, and many of you may have read this. The late astronomer, the science communicator Carl Sagan wrote a very moving caption for this pale blue dot, and the caption reads as follows. Okay, so I'll just leave the screen here for you to read. These are very powerful words from very poetic words also from Carl Sagan. And so I think the images like these, remind us that we are living in a truly vast universe, and it puts a lot of things in perspective. Okay, so I think once in a while it's good to stare at an image like this and realize, where we are in the vastness of the universe. So that is Earth seen from the distance of Pluto. So you can imagine taking direct images of extrasolar planets, how difficult it is, because even the planets within our own solar system, when seen from the fringes of the solar system, they look very tiny. I just want to leave with that. Okay, thank you all for listening. And
Thank you, sir, for your time.
yeah, okay.
Thank you for those bonus slides too.
Yeah, sure. Okay. Have a nice weekend, all of you.
Thank you, sir.
Thank you, sir.